There we go. We're live. And let's go to the grade 12 notes booklet by the, let's see, where's the class here? There we go. And okay, that's where our quiz was. Go to welcome. Oh, it's not in welcome. There it is. Chapter 11, Perms, Coms, and the Binomial Theorem. Okay, so here we go. Permutations with constraints. 5 people, Alvin, Barry, Calvin, Daryl, and Ernest, A, B, C, D, and E, are seated on a bench. How many ways can they be arranged if E is seated in the middle? So I would actually draw this out. There is 1, 2, 3, 4, 5 seats. Ernest has to be in here. There is only one Ernest. So he has to go there. There's only one way to put that person in that seat. But what about the other 4 seats? Well, there's still 4 people to choose from that could go here. There's still 3 people to choose from that could go there. There's still 2 people to choose from that could go there. And there's still 1 person to choose from that has to go there. So it's 4 times 3 times 1 times 2 times 1. Or does that look familiar? That's 4 factorial, which is 24. Now, what if I have 5 people that are going to sit on a bench, but A and B have to sit next to each other? That's a constraint. You can put everybody else anywhere you want, but A and B have to sit next to each other. Oh, and it doesn't say they both have to be on an end, or one of them has to be on an end. They could be next to each other at the end. They could be next to each other in the middle to the left. They could be next to each other in the middle on the right. That seems like it's added a lot of complication to the problem. But actually, it hasn't really. There's kind of a trick here, a technique here. What you do is you treat A and B like one person. In other words, you treat them like one object. So instead of 5 objects, oh, that's a mistake. Instead of 5 objects, the set now has 4. So, no problem. Isn't that 4 factorial? How many ways can I arrange 4 things? Well, there's one trick though. If I treat A and B like it's one object, yeah, 4 factorial now. But it doesn't say that A has to sit on the left and B has to sit on the right. For every one of the arrangements where A and B sit next to each other, there's the same arrangement, but A and B switch spots. So I should probably put a factorial on that. So it's 4 factorial, which is, again, arranging 4 things, and 2 factorial, since it could be A, B, or it could be BA, right? So 4 factorial times 2 factorial is 24 times 2, 48 ways. Now, what do you think of this? How many ways could I arrange it so that 5 people can sit anywhere on a bench except A and B can't sit together? So now instead of A and B have to sit together, they have to be apart. Now that doesn't mean they have to be on the far ends. It could just mean that there's only one person between them. It could be that there's 2 people between them. Ooh, again, this sounds complicated. Right.
Maybe there's like a 50% chance that A and B are next to each other, so you try to divide.
Yeah, but next to each other, what does next to each other mean, right? Right? Because think, we could have one person. So should I count all the cases where A and B are at the ends? And then all of the cases where A is in slot 1 and B is in slot 3? Actually, there's a much simpler way. Have you figured it out? The people at home probably couldn't hear that in the mic, but it's the perfect answer. Didn't we just figure out all of the ways where they could sit together? Why don't we just subtract that from all the ways they could sit, period?
Factorial minus.
There it is. So 5 factorial minus the answer we just had, which is 48. So again, what does this mean? This is total number of arrangements. And this is arrangements. Apparently I can't spell arrangements. Arrangements where A is next to B. So this would have to be all the ways where they're not next to each other. So that's 120 minus 48, which is 72. I don't expect you to memorize that 5 factorial is 120. And then 6 is 720, and then after that I don't remember. Okay, any questions about that? Or how we did that? All right. Want to try a couple on your own here? I'll pause the video so that people aren't sitting there looking at dead air if they're watching this on YouTube. And we'll give you a couple minutes. This is one of those places where I'd love to be able to put you together in teams and think this out, but we're not supposed to move the desks. So, but still, you feel free to talk it out amongst yourselves here. Let's give you a couple minutes to try A, B, and C here. Your page has an A, B, and C, right? Okay. So let's give this a try. I'm going to pause the video, give those 3 questions a try. Okay, here's what we get. If there's no restrictions whatsoever, obviously, there's 12 factorial, right? You can arrange those 12 books any way you want. Doesn't matter what order they're in. And take a look, 12 factorial is a huge number. It's 479 million and change. But if they must be arranged by subject area, do you get where I'm getting this answer from? I'm getting this answer in that this is, of course, all of the ways to shuffle the 3 calculus books, but they have to be together, right? So all the calculus books have to be together. So there's 6 ways to arrange the calculus books. Then there's 5 factorial ways to do the bio books. And then there's 4 factorial ways to do the economics books. And then, what do you think this 3 factorial is for? Right. It didn't say what order the subjects had to be in. It could be economics, then calculus, then bio, or calculus, then bio, then economics. You get the idea. I don't know why that popped up. This is ways to arrange the subjects. Does the logic of that make sense? A significant amount of this chapter is about reasoning skills, which is another reason why I like ending with it. It's kind of a fun thing to end with. All right, for C, how many ways can you arrange the books if all the calculus books must be on the right-hand side? Well, I'll do that first. So this is the calculus books. They all have to be together and they all have to be on one side. But it didn't say anything about the rest of the books. It didn't even say that you had to separate bio and economics. So that's why it's basically the rest of the books. And again, you get a pretty big number, 2 million and change. Numbers get unbelievably big when you're working with factorials. How many people know how to solve a Rubik's Cube? How many people here can solve a Rubik's Cube if you give? I'm okay. I need about 5 minutes to solve a Rubik's Cube. I'm not one of those guys, speed freaks, who can do it in seconds. Do you know how many possible arrangements there are on a Rubik's Cube?
Has to be like 9 on each side, so there's 6 sides. Probably a billion.
Way bigger. It's a number. It's unfathomably big almost. And what's cool is that the Rubik's Cube's been around since the 70s. And of course, those guys who can do the Rubik's Cube super fast, they're you know, what they're doing is most of them are doing an algorithm. Most of them, that's how I solve the Rubik's Cube. Basically, I solve one side, and then I'm basically following a pattern that I memorized that somebody taught me. And then you could even do it with your eyes closed. You'd have to peek every once in a while to see when you're done. But there are people who can do them with their eyes closed. but you have to have one side first. There's an algorithm. So some people are doing it kind of by algorithm, and they're just going really fast. But, of course, if you were omnipotent and omniscient, you would be able to see the absolute fastest way to solve a Rubik's Cube, right? If I mix up a Rubik's Cube and hand it to you, maybe you do it in 30 moves, and I mix the same up, so it was exactly the same arrangement when I hand it to you, and you did it in 26 moves. What's the absolute most that you could mix up a Rubik's Cube so that a person who is omniscient and omnipotent would know the perfect number, smallest number of moves to mix it up? And Rubik's Cube's been around since the 70s. They just figured this out a few years ago. It was in the 2000s. The number's 20. God's number, they call it, for the Rubik's Cube. If you were a god who could look at the Rubik's Cube and I know the smallest number of moves possible to solve this Rubik's Cube, it is impossible for you to mix up a Rubik's Cube past 20 moves needed to solve it. And the math that they did to figure that out was beyond what you could do even probably on your ordinary laptop, desktop computer. The numbers got enormous. They had to crunch numbers. Anyway, there's a cool video on that I could show you, or I could put a link to it. All right, so this is what we called, what do we call this again? Constraints, right, is what they use? Yeah, the word they use is constraints. The next complication to permutations is called cases. What if we have different cases? For example, every example we've seen so far is a permutation with one case. But sometimes it's impossible to summarize all possible permutations into a single equation. If you cannot summarize the situation, you must break the situation into distinct cases. For example, the letters ART, EF, QU are to be arranged in a row, but the arrangement must begin and end with both consonants or both vowels. How many ways can this be done? Check this out. If you begin and end with consonants, okay, first of all, we're arranging, how many letters are we arranging? We're arranging 1, 2, 3, 4, 5, 6, 7. So I'm going to actually put 7 blanks down. 1, 2, 3, 4, 5, 6, 7. 7 blanks. How many ways can you do this if you begin and end with consonants? First of all, every year I have people who don't know the difference between a consonant and a vowel. Does everybody know? Consonants are the R, T, F, and Q. Vowels are the A, E, and the U. So this here has to be R or T or F or Q. So there's 4 things this can be. That means down over here, since I've already used one of them, there's 3 things this can be. So this is the R, the T, the F, or the Q, but minus 1, right? Because I already used one of them. After that, do we care what happens with the rest of the cases? No, the rest of the letters can be random, doesn't matter. So now just add them all together. I've used 2 of the letters. There was 7 to begin with. So there's 5 that can go here, 4, 3, 2, and 1. So if you want to break that into easy to digest math, notice that from here to here, that's 5 factorial, and then times 4 times 3, which is 5 factorial times 12, which is 120 times 12, which is 144 with a 0 on it. That's not the answer yet. That's only case 1. Case 2 begins and ends with vowels. Now, if you're wondering, well, why couldn't you just do this in the same equation? Just slap another multiply on here. Because, check it out, for the 7 cases, it isn't 4 at this end anymore. Now it's 3 at this end, right? And it isn't 3 at the other end like it was the first time. Now it's 2 at the other end. Get it? This can be I, E, or O. No, sorry, A, E, or U. A, E, or U. And this can be A, E, or U minus the one that you used at the other end. So this is 3. And then the middle part's the same. 5 times 4 times 3 times 2 times 1. So this is 5 factorial times, this time, 3 times 2. So this is 120 times 6, which is 720. In sum, there are 1,440 ways to do it with the consonants at the end, plus 720 ways to do it with the vowels at the end, which is 2,160 possible permutations. All right. Here's a classic for these kinds of things. And for those of you who ever want to think about things like cryptography, this kind of stuff is very important, right? How many different passwords are there? How many different ways can you arrange numbers and digits to make a unique thing? Example, how many different 3-digit even numbers greater than 303 can you make using those numbers? No digits are repeated. So once you've used the 3, you can't use the 3 again. You can't repeat the digits. So case 1, what are my cases here? Well, greater than 303, but it also has to be even. So let's think about this. What is case 1, case 2, and case 3? Any idea? Case 1 is that we end with a 2. Case 2 is that we end with a 4. And case 3 is that we end with a 6. And very often here when I'm doing this example, I've been doing this example for years, somebody will say, I've had this question, how did you know those were the cases? How did you know that the cases weren't, hey, I have to count the things that are bigger than 300, bigger than 400, bigger than 500, bigger than 600? How do you know those weren't the cases? And the answer I give to that is, well, because I can group those into one case, right? You're bigger than 303, and then all of the other cases past that are bigger than 303. I can lump that into one condition. But I can't lump these into one condition because if my 4 is at the end, then I can't use a 4 at the beginning, which changes how many I'm counting that are bigger than 303. If I put my 2 at the end, I don't have to worry that the 2 is at the beginning and I have a number that's smaller than 303. See the problem? The end number is what dictates my cases, not the beginning number. So let's take case 1. We end with a 2. So I have a 3-digit number, digit, digit, and this has to be a 2. Well, there's only one 2. So there's only one possibility there. But how many things could go here? Can't the 3 go there?
No, only 4 and 5.
What?
4 and 5.
Can't the 6 go there? Now, I know people thinking, well, wait a minute, maybe the 3 can't go here because we have to be bigger than 303. But wait a minute, if I put a 3 here, isn't all of my choices bigger than 303? Because there's no zeros in my choices. So this can be a 3, a 4, a 5, or a 6. There's 4 different digits that can go there. Okay, now, logically, I used one of my digits here. I already used the other one of the digits there. I had 6 to choose from. There's 4 left. So this case is 16 different ways, 4 times 4 times 1. Case 2, if we end with a 4, well, again, there's only one 4. But what's the first one? Now it can only be 3, 5, or 6. So this is 3 times 4 times 1. See how the number has to be counted as a different case? It works out differently. So that's 12 different ways. This one actually does work out the same as the other one, right? If I put a 6 at the end, there's only one way to do that. And now I can choose between 3, 4, and 5 here. There's 3 different ways I can do that, and 4 in the middle. So my total is 16 plus 12 plus 12. So my final answer is 40. There are 40 3-digit numbers that follow the rule that they're bigger than 303 and they're even. Okay? All right. Once again, we'll pause the video, and people at home, and you guys can give this a try. Let's try this for a couple minutes. See if you can come up with your own answer. This time I won't let you watch me do it. So hang on, I'm just going to pause here. Okay, the pause. Okay, we're recording again. Did you get... Come on, screen. 21. And do you see where I got 21 from? If I end with a 5, there's 3 things I can use for the first digit and 3 for the second. Remember, I can't use 0 as my first digit. That wouldn't make a 3-digit number. Case 2 ends with a 0, so now there's 4 things I could use for the first digit. 2, 3, 5, and 8. Still 3 things I can use in the middle digit. Does everybody get how I got the middle digit of 3? Right? Because there's 5 digits to choose from, and I used 1 on the first one, 1 on the last one. That leaves 3 to choose from in the middle. Okay? So the middle in both cases here is kind of the rest of what's left over after I've chosen the beginning and the end. All right. Question?
Couldn't 0 be a middle number if it ends in 5?
Yeah. Right?
Oh, okay.
Yeah. There's still, right? I've chosen one of these. Notice it's not a 0. So the 0 is one of these 3 numbers that's left over.
Oh, got you. Yeah.
Right? Oh, sorry, I meant in the first one. Yeah, in the first one. Right? I've chosen a 2, a 3, or an 8, so 2 of those are left over. The third thing that's left over is the 0. Yeah. Okay. All right, any other questions about this? Okay, yeah, we just answered that question, person in the chat there. Yeah, okay, good. Okay, so there we go. That's basically how these work. So now that we've covered this, now that we're done this, everything in chapter 11.1 now should be basically doable. So I'll let you guys have a little bit of work time, actually. You can work on trying to get some of these 11 questions done. Is there anybody here who still owes me the quiz from last week, from Friday? Was it Friday or Thursday? No, it was Friday. Friday. Anybody owe me the quiz from Friday? No, I think so. I think I had perfect attendance. Some people were late, but I think everybody got here. Okay. All right, I didn't even start marking yours. I thought I better do the grade 11s first. So I'll probably need, if not finishing them tonight, for sure finishing them tomorrow. And then they'll be done. Okay, I'm going to stop my video. That's it for the rest of the lesson here on permutations. Tomorrow we start combinations.